Hey everyone, in this video, let's take a look at question 79, word search on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, we are given an m by n grid of characters, which we call board, and a string word, and we want to return true if word exists in the grid. The way we can form word is essentially by either looking to the right-hand side, left-hand side, up, or below. So basically we can look in adjacent cells where adjacent cells are joined horizontally or vertically and they're neighboring. The same cell may not be used more than once. To put simply, we want to find, using kind of like a word search method that we're used to, whether the word exists in the grid or not. The main difference here is that we can't look diagonally, and it's not just horizontal and vertical, but it can be both of them together. So that's the main differences here. You can see here that we can form this word A, B, C, C, E, D, just like this. In this grid, we can form S, E, E, just like this. And in this grid, we can't form anything actually. We can't form A, B, C, B. It does not exist. So how might we go about doing this question? Well, even before we start, anytime you see like a grid type question, then we have our basic grid algorithms. We know breadth first search and we know depth first search. And in this case, it looks like we need to use one of them. Well, which one might be better here? Well, I would argue that depth first search actually might be better here. And the reason for this is because if you realistically think of a word search, right, it's possible that your word is just along any single row, right? Your word might just be completely along the second row. And if your word is pretty long, then depth first search will find that answer much faster than breadth first search will. BFS will look level by level, whereas DFS try to explore as much in one direction as it can, as long as it's still valid. So let's maybe try a DFS approach here. And we know our basic template for DFS. We've done it in our number of islands question. So we can maybe look at that one or seem to follow that one. So let's maybe go ahead and start off writing our code, and then we can walk our way through any of the problems that we run into. But as with any of these types of questions, first of all, I'd like to rename this to grid, and I will just rename this to target to kind of, actually, I think I can keep this word. So one of the things we need to do is we need to keep track of where we are in the grid. So remember, we always perform DFS based on a specific location in the grid. So we need to loop through the grid first. So I will determine my rows and my columns like so, with length of grid and length of grid at 0. And then I will loop through them for column in range protocols. Okay, so now I am looping through this grid here. Now, if you recall in the number of islands question, we began a DFS search the moment we figured out that we were on a number 1, which is the start of an island. Similarly here, we can begin our DFS search where, well, it wouldn't make sense to just do a DFS search from every single letter, right? Because we don't need to. If a word here begins with an A, then the only places we need to do a DFS search from is where A is in the grid. So we can actually just check for that. We can check if grid at row call is equal to word at 0, equal to the first letter, then we can do our DFS call here, right? And what do we want our DFS call to return? Well, why don't we just return whether or not we could have formed the word or not. So if we could have formed the word, then it will return true. So if my DFS call, if this returns true, then I know that overall we have found our answer. If it doesn't return true, then maybe there's another location, like maybe here this A doesn't return true, but maybe this A will return true. So we can try looking at that one. If none of them work, then we know that we have no solution, so we can return false here. Okay, so now we have our basic method of the DFS. Now let's take a look at what we might want to pass in, okay? So I'm just going to pass in the basic stuff, and then let's write our way through the DFS method, and we can see a couple of the things that we need to add. Okay, so one of the things we'll need is we'll need the grid, we'll need the current row, and we'll need the current column, and we'll need a couple of other things as well, but let's kind of just start off with this. So one of the first things we want to do in a DFS is, or any really sort of grid problem, is we want to make sure we're not out of bounds. So the way we could do that is we could first of all calculate the rows and the columns. And again, we've done this same type of method in our numbers of islands. So we'll calculate the number of row and the number of columns. Now we have our general formula to just make sure we're in bounds. So we can check if row is less than 0, or row is greater or equal to rows, or column is less than 0, or column is greater or equal to cols. If this is the case, then we're basically outside of the grid, right? We're either out here, out here, out here, or out here. So we will not consider this. Okay, so now that we have that basic check done, what do we need to consider? Well, if you think about this, let's say we're starting off at this A over here, right? we're starting off at this A over here. When we are doing our DFS call, it would really be helpful for us to not explore letters that we don't need to necessarily explore, right? For instance, let's say that if we go to here, if we start off at A here, and then we go to this S, well, we can see that it's already not a match, right? Because our word is A and B, and this is A and S. So it doesn't even make sense for us to maybe go from A, S, F, and then just keep going, because we're already broken at the second step here. So in that sense, it's kind of helpful to keep an index of where we are in the word, because if we ever come across a scenario in which maybe index here would be we're at the first index. So if index at 1, or if word at 1, which is a B, does not match like the current cell here, then we know we're automatically not going to have a match. So we can maybe keep track of that as well. So we can do like index. And so what we can check is we can check if grid row and column does not equal, well, we need access to the word as well, right? The target word does not equal word at index, then we can automatically return false, right? Basically, if we're at a S over here, which is index 1, then that does not equal the B over here, so there's no point in looking forward. Okay, so we have these two cases and we're filling up our parameters, which is good. Now what else might we need? Well, we need a stopping condition for the true case, right? Like how do we know that we have successfully found the word? Well, if you think about it, what we really need to check is if this is already checked, then at this point we know that at least we are following the correct path, or we are following a correct path. So now we are at A and B, for instance. How do I determine if I am at the end of the word? Well, assuming that we pass this, what we can basically check now is I can just check whether my index, like the number that it is, right? So for instance, here we have 1, 2, 3, 4, 5, 6. If I can determine that my index is 5, then I know that all of this has already passed, and I know that this here must be a D, and if my index is 5, then I know that I have created a word that is 1, 2, 3, 4, 5, 6 in length. So then I'm actually at my end case here. What I can check is I can check if index is equal to length of word minus 1, then it's true. Because at this point, I have figured out that every single word, every single letter has been correct throughout the indices, and even the last one is correct, and I'm actually at the last one here, which is this index here, index 5. So in this case, we can return true. Now we're pretty much almost done. All we need to do now is recurse. So which directions can we recurse in? Well, because we can go horizontal and vertical, it means we can recurse left, right, up, and down. So let's maybe define that in a couple of variables here. So grid row call word index. And I will actually just paste this again and again. So left, right, up, and then down. So let's figure out what all of this should be. So the row and call, well, if you're going left, the column decreases by 1. If you're going right, it increases by 1. If you're going up, the row decreases by 1. If you're going down, the row increases by 1, right? Do we need to change anything else here? Well, if you think about it, we do need to change one more thing, and that's actually the index. Because the index, once we make a turn here, we will be going one more location, right? We will be going one more, like one more step. We will be adding one more letter. So we need to increase the index over here as well. So we'll do these for all 4. Right? So index plus 1. Okay. And now what do we need to return? Well, assuming we're at, let's say, the A over here, and we look in all 4 of the directions, if any of them return true, then I know that I have arrived at my solution. So I can just return left or right or up or down, right? So this is pretty much it. Do we need anything else? Well, if you think about it, we actually do, because in DFS, one of the problems is that we might visit the same location twice. For instance, if we're at the A and we go to the B and then we go back to the A, like let's say your word was like ABA, right? But we can't go right and then back because then we're reusing the same word. So we need a way to basically mark our cell as visited or as seen, right? What we can actually do is something we did in the number of islands, but basically just before we do a recursive call, we can mark our grid and row with the like something that doesn't exist, right? Like let's see here. So it looks like all of these will be letters, right? So just uppercase and lowercase English letters. So let's just maybe mark it with something like this, right? And then when we are done, when we are done a recursion, we have to make sure to set it back. So here we will do grid row and call, and we need the original letter, so we can actually just say OG is equal to grid row and call, and then here we will do OG, right? And now what happens is that when we are at the A, we mark the OG as A, so this becomes A, this becomes A. Then we go ahead and mark it as the tilde sign, and then let's say we go right, and then eventually we go back left. Well, we need to add a check to see if we see a tilde sign, then that basically means we've seen the variable, right? We've seen the letter. So we can do something like that. So we can do if grid at row call is equal to the tilde sign, and I can just return false. And I will actually just put this before here, right? I will just put this before here. And we need to make sure to unset it. We need to make sure to unset it back, because what can happen here is, for instance, if we do A, B, C, E, once we go back to the C, or let's say actually we do A, B, C, E, S, and then finally the C here. Well, all of this will be marked as tilde, right? But when we go back, we need to unmark this C as whatever it was, which is just the C. Because if we go back here, then we go back here, then we go back here, we need to be able to go down. And if this was a tilde, we wouldn't be able to do that. So that's why we need to mark it back, and that's why we mark it as OG back here. So after this, all we really need to do is fill out the set of informations here. So what do we need to fill out? So we have grid, row, column, word, and index we can start off as 0. So now let's go ahead and try this out to see if it passes. And it does. Let's go ahead and submit it. And this one, even if it is the correct answer, it looks like they have a couple of test cases, so it will take quite some time, but you can see that this also does pass. So this is the DFS way of doing it. For the time complexity, basically, I would say that it would be O of m times n, so rows times calls. And for the space complexity, space is kind of the same thing here if you want to consider recursive stack space. But since we aren't storing anything like in a variable or anything like that in an array, we don't have really any space complexity to worry about. So that was this question. I hope you learned something.